So, hello, welcome to the graphics programming virtual meetup. Today we will talk about parallel prefix sum, or we also call this algorithm scan with CUDA. So I think nowadays, because this algorithm is so used in everything that nowadays there are intrinsics to do this, but it's still cool to learn. I guess to learn how it works as an algorithm, I guess. So parallel prefix sum, also known as scan, is a useful building block for many parallel algorithms. So this document introduces scan and describe step by step on how to implement in CUDA. So we don't have our resident AMD expert here, so we don't know how it compares, but let's see. So first, an introduction to what prefix sum is. Have any of you used like C++ STLs, like this algorithm before?
A prefix sum one?
Yeah, also C++ have three algorithms. A prefix sum. I don't think it calls prefix sum in C++. It's called something, and then there are also inclusive scan and exclusive scan. Like C++ have three versions of the same algorithm for this. The basic idea is like you just add for each element like this. For the first element, it's the same. For the second element, it's the first plus the second, and for the third, it's the first plus second plus the third, etc., etc. So like this. Yeah, partial sum.
Yeah, I had no idea they had this by default.
Yeah, C++ had three forms because partial sum unfortunately is specified in a way that can't be paralleled at all. Like in here, it's specified in a way that order is important, and then this one does not consider order, so it can be parallel. And this one is just a slightly different algorithm, which we will talk about later in here. So yeah, there are a lot of uses for prefix sums, like sorting, lexical analysis, string comparison, polynomial evaluation. I don't even know those applications. The string compaction is very commonly used when string compaction is just basically it's just remove if, or I guess it's copy if. So the idea is only copy elements satisfy certain criteria. And you can think about how this can be useful in things such as ray tracing. We, for example, only copy the paths that haven't been terminated. And so then going to a second path, for example. Anyway, so basically sequentially we will doing this. We just set the first. No, this is the exclusive version, because this is the inclusive version. Now, I guess for the exclusive version, we set the first element to 0, and then for others, we just add. And we can parallelize that, but this is just pseudocode.
How does that work? I don't understand. The parallel version.
And then we'll talk about it later.
Oh, okay.
Yeah, but I guess here the big idea is like you can't not do it infixed. Not infixed. What's the word? Like you cannot do it in place. You need another buffer. Copy to another buffer.
Okay.
So yeah, there are two versions. Like Prefix Sum is also known as scan, which come from APL. And so there are two versions, the inclusive scan and exclusive scan, which is slightly different. Like this version is inclusive version, and for exclusive version, the first element is identity, and the second element is the first original element. The third element is the first plus the second. So like this. And the last element in the original array just get dropped, never get into the result.
Wait, why would you ever want to just ignore the last element?
Because it's exclusive, right? It's not included. It's like, yeah, it's not including itself, right?
Yeah.
Okay.
I guess both inclusive and exclusive can, like, they are not by themselves very useful. Just they are building blocks for other algorithms.
And also, aren't they just shifted by one? It's like the same.
Yeah, it's just shifted. It's trivial to convert inclusive and exclusive scan to each other. Yeah.
But sorry, wait. So like, then yeah. So in that example, that 3 there at the end, that just never gets even added to the.
No.
Like it's weird
yeah,
that you just completely drop one of the
this
elements.
is, yeah, you can say this is 6, right?
Yeah.
And this just gets dropped.
It's like, why? That just seems weird to me that you would ignore the last value.
Yeah. Well, how it's useful, I'm not certain, like why you would want to do that.
I guess, is this just a constraint of the algorithm, and so you should put garbage data in the last element?
Yeah, you can just put a 0 in last element. It doesn't matter.
Okay.
Yeah, because it's exclusive of itself, right? So, but I'm not sure how it's why that's useful.
Yeah.
That's
And maybe we'll get to that, hopefully.
Yeah, I don't think so, because yeah, this paper is all about implementing that. Yeah, but it's also like just exclusive and inclusive. They are basically the same algorithm. Just you can just shift by one. But I guess exclusive is easier to implement, because afterwards, for the remainder of the paper, we'll focus on exclusive scan. And
and the first
inclusive
element is
probably-
always 0, right? The last element is dropped in the original array, but the first element in the result is always 0.
Yeah. All right, and for the sequential version is just trivial. It's a for loop. So we have input and output and the length. I don't know why they put it in this order, like outputs before input, but anyway. Anyway, it's a for loop. We set the first element to 0. And for the other elements, we just add. So this code performs exactly n adds for an array of length n. And we say this is the minimum number of add required to produce a scanned array. And when we develop our parallel version of scan, we would like it to be work efficient, which means we do no more addition operations or work than the sequential version. So because sequential version do n add, we want to also do n add. In other words, the parallel version should also be on. So the first algorithm introduced is not work efficient, this naive algorithm that because it perform the scan in log n passes, and for each passes it will do an add. It will do certain number of adds. So as a result, we will have a on log n complexity. I guess how it works is where's the graph? Yeah, I guess in here, this shows how this algorithm works. We just add the two elements, add the neighboring elements, and then in the second pass we add every 2 elements, and for the third pass we add every 4 elements. etc., etc.
So you have a bunch of sync points, I guess. So you do a bunch of parallel work in passes.
Yeah,
Okay.
yeah. See, we have sync point here.
Oh yeah. Interesting. What is K in the pseudocode? Is that the number of threads or no? That kind of,
Yeah, I think it's number of elements.
oh right, yeah, yeah. Okay, cool.
I guess I didn't pay too much attention of how this works because this is just a bad algorithm. When I read this, you just look at the graph and I kind of have an idea how it works, and that's it. Yeah, so this algorithm assumes there are as many processors as the data elements, but GPU is not the case. So instead, we have those small warps. And because not all threads are run simultaneously for array larger than warp size, the algorithm above will not work because it performs scans in place. And so instead, we can't do it in place. We need double buffering. And this version basically do double buffering. We have a swap buffer here. Not swap buffer. What this does? This just copy one buffer to another buffer. Oh, yeah. I guess swap buffer is here. And this is the actual code. We use shared memory. Now let's talk about the extra interesting stuff, which is the work efficient parallel scan. So this algorithm uses the idea of a balanced tree. And there are two passes. We first sweep it up and then sweep it down. I guess it's here. The up sweep phase and down sweep phase. But anyway, a binary tree with n leaves have log n levels, and each level has 2D nodes. And if we perform one add per node, then we will perform the OM adds single traversal of the tree. Also, we don't actually build a like tree data structure. Instead, we just has a concept of a tree, or we can see the tree is in place inside the array. And yeah, the upsweep phase, as we will say, is just a reduction. Do they have a, I guess they don't have numbers as demonstration, but just the upsweep phase is like we first add those two together to here, add those two together to here, add those two together, add those two together, and then add those two together. And then add those two together to the final result. So it is kind of a reduction because the final element will be the sum of all the elements, but we also leave a lot of other elements in place. I guess it's easier to say if they have actual numbers, but yeah, and they don't.
It's weird that I might just be reading this wrong, but it says like for d equals 0 to log n minus 1, but then but d equals 0 in the diagram looks like it already has all the answers in it.
Yeah, I think it's from here, from d equal to 3.
Okay.
Yeah, from downward to upward in this diagram.
Right. Okay.
And yeah, the down sweep is the very interesting one. We set the root to 0, and the 0 will propagate left until it becomes the first element. And then for each pass, we consider the array as a binary tree, and then we say for the parent in the first pass is just 0 element of just the last element. For the parent, we say set the left child to the parent's value and set the right child, which is actually just the parent in slot itself. But that's why we say it's conceptually a binary tree. We don't actually have a binary tree at any point. For the right child, we set it into the previous value of the left child.
I feel like I want to see this drawn as an actual tree.
Yeah, I don't get this.
I guess yeah, it's drawing as a tree like in here. right? It's like root. You have 2 children, and you have 4 children, and 8 leaves.
Right.
Yeah, but actually, like it's a binary tree in time. So like, this is just one array. That's the
Yeah, I
interesting
see.
part.
What does the blue arrow stand for?
What?
The blue arrow, you know, there's a like
That's
D0.
adding, right?
We just copy it into here.
Or isn't that adding it?
Oh yeah, add it to here. Sorry. Yeah, it's adding. So yeah, so here is 0 and 3 and 4 to 5. We added. Yeah, for this one it's add.
Oh,
For this one it's
okay. Okay.
Yeah, it just looks like it's copying. The first one's 0.
yeah. Yeah, this is the actual code. The actual code is just basically a lot of playing with indices, basically. Not as interesting when looking at it. It's pretty easy to get wrong when writing ourselves. Okay, I guess for the previous section, it's pretty generic stuff, just how the algorithm works. For this section, I am not sure about other GPUs because bank conflict seems very NVIDIA stuff. So the idea of bank conflict is that shared memory has multiple banks, and when we access the same bank, and if we access a different slot in the same bank, it becomes serial. We cannot access that in the same time. So it's kind of like CPU cache. CPU cache has something similar, but I learned it too long times ago. I forget how exactly that works. Yeah, but anyway, because we only have a very limited number of banks, it's really easy to have this kind of conflict. And for the binary tree algorithm, like our scan is tricky because we doubling the number of threads that access the same bank. Yeah, doubling the stride. So as a result, we oh. As a result, for deep trees as well, approach the middle level of the tree, the degree of band conflict increase, and then it decrease again. And yeah, even for a 512 elements array, we can have like 16-way band conflicts, which is really bad. So for like easier stuff, band conflict can usually be avoidable. For easier stuff like convolution, we just can just pad the memory allocation with something, and then it's solved. But because we have a balanced tree approach where we increase the stride in each passes, so it's not that easy. So instead, we add a variable amount of padding to each shared memory array indices. We add the index to we add to the index the value of the index divided by the number of shared memory banks. I don't know why they have these two versions, and did they explain that? Yeah, but anyway, I think they basically just add an offset.
So you're saying you think this might be very NVIDIA specific?
Yeah. Yeah, because I haven't heard this thing in other hardware, but maybe there are also this. But I definitely know this impacts NVIDIA's performance a lot.
Okay.
Yeah, even nowadays. Yeah, I guess the last part is like our current version only works with a single thread block. We just use the single thread block with shared memory. We haven't scaled it up. But for large arrays, we can divide the large array into blocks, and we can scan the single block. But after scan the single block, we also write the total sum of each block to another array of block sums. And then we scan that block sums, which generates an array of block increments. And then we add it back. Also, for non-power of 2 dimensions, we just simply divide the array into blocks like before, and for the last block we initialize it with extra zeros. Yeah, so the process is we scan each block, we add the sum of each block to this array. We scan this much smaller array, and then we add as a result the block sum back into each blocks. So at the end, performance, I guess nowadays is much more different than this. This paper is like in the infancy of GPU computing, but yeah, even at that time, with 6,000 elements, we also already see a speed up. And yeah, when we have millions of elements, it's a huge speed up. But still nowadays, I will expect 100x, not like 5x. Yeah, and that's this paper. Any lasting questions about like this or previous stuff?
They don't have the code for this, do they?
The code?
Is it just in the paper? You have to kind of just copy it out.
Yeah. I think they probably have the code. It's just you need to find it somewhere.
Let's see.
But also, if you want to implement this yourself nowadays, this is not state of art. So you definitely need to do more search.
Oh, I found it. Just Google. There's a GitHub repo. Well, yeah, I can just.
Yeah, also this is a really good read. I also read it. No, yeah, nowadays we definitely have intrinsics, so it's kind of a different story.
So you can like, are you just like it's built in doing prefix sums?
Yeah,
It seems very useful.
yeah, but also still complicated. I think even more complicated nowadays because because just all the modern hardware complexity. Oh, single pass. Single pass is definitely better than what we described here, which have multiple passes. Yeah, maybe we can read it someday.
Yeah,
Or
I'd
at
be
least I can
curious.
read it.
It sounds like from that Linus Revian article, it sounded like not like this works well with CUDA, but some of the memory models of like Vulkan and stuff and compute shaders maybe are make this a little tricky to implement. I haven't read in too close detail, but
Yeah, memory model is this kind of stuff that I understand very poorly. But also, I don't expect many people to understand that, so I'm not ashamed.
Yeah, definitely.
Stop the recording.